A cosmic alignment so perfect it defies chance, or a deliberate arrival we were never meant to see. On September 12, 2025, astronomers witnessed the impossible. Two colossal objects arriving from opposite ends of the universe, set to rendezvous in our solar system during a total observation blackout. The official story is twin comets, but the evidence points to something far stranger. Let's explore this together. Swan's dramatic arrival. What if a new object appeared in the sky tonight, so large it dwarfed everything we've seen in a generation? That's exactly what happened on September 12, 2025. Data from the Solar Wind Anisotropies, or SWAN instrument, a wide-field camera aboard the SOHO spacecraft, revealed a bright, unmistakable object blazing through the solar system. The initial readings were staggering. Its tail stretched nearly 2.5 degrees across the sky, which is about 5 times the width of a full moon. For a newly discovered comet, this scale is almost unheard of. For comparison, the famous comet Hale-Bopp's tail was about as wide at a similar distance. Initial photometry clocked it at a magnitude of 7.4, a brightness level that makes it an easy target for backyard telescopes and even powerful binoculars. The news spread like wildfire, and amateur astronomers scrambled to confirm what the satellite had seen. Just 2 days later, an observer in Australia captured a dramatic image showing a streak of light so immense it barely fit in the camera's frame. The immediate reaction wasn't just excitement, it was disbelief, as the object was already outshining professional predictions by a factor of 4. This was no ordinary icy visitor. The sheer size and luminosity didn't match any recent precedent, forcing comparisons to legendary comets of the past. Official recognition and growing mystery. A name makes it real but can also deepen the mystery. By September 13th, the International Astronomical Union's Minor Planet Center made it official, designating the object C/2025 R2 or SWAN in honor of the instrument that found it. Within a single weekend, the global astronomy community, from professionals using the Hubble Space Telescope to amateurs in their backyards, was completely fixated on this celestial titan. They traded images and brightness measurements across hemispheres, trying to make sense of its unprecedented behavior. Most comets discovered in the modern era are faint smudges requiring powerful telescopes, but SWAN was a spectacle for anyone who knew where to look. Its magnificent tail sliced through the constellation Virgo at a blistering pace of 20 arcseconds per minute, growing brighter with each passing day as it raced toward the sun. The conversation quickly shifted from simple observation to intense speculation, with astronomers like Dr. Robert Warwick, the discoverer of Oumuamua, noting the statistical improbability of such a bright object appearing with so little warning. The amateur community, often the first to notice unusual behavior, was already debating what could possibly power a tail this long and this bright. It was simply too big, too vivid, and too fast to be ignored. The cosmic coincidence. Some things are too perfect to be random. C/2025 R2 or SWAN wasn't the only newcomer drawing attention. Just days before its discovery, another object, the Interstellar 3 I/Atlas, was already on its way in, approaching from a completely different sector of the sky. SWAN's path originated from the direction of Aquarius, while Atlas emerged from Sagittarius. On a star map, their arrival vectors are separated by more than 100 degrees of the sky. And yet, both are scheduled to reach perihelion, their closest point to the Sun, within the same 10-day window in October. SWAN will arrive around October 20th at a distance of about 1 AU, the same as Earth's orbit. Atlas will skim past the Sun just 3 days earlier on October 17th, at a distance of roughly 1.36 AU. This puts their perihelion points only about 50 million kilometers apart, closer than Mars ever gets to Earth. Their orbital geometry is just as striking. Both are on steeply inclined paths, with SWAN tilted over 60 degrees and Atlas at a near-polar 85 degrees to the plane of our solar system. According to experts like Dr. Paul Chodas at NASA's Center for Near-Earth Object Studies, the odds of two such objects from such different origins, arriving in near-perfect synchrony, are vanishingly small, estimated at less than 1 in a billion. Atlas breaks the rules. So, what happens when an object just flat-out refuses to follow the laws of physics as we know them? Well, 3I/Atlas first caught astronomers' attention by, honestly, breaking all the rules. Early spectrographs from the Atacama Large Millimeter Array reported something that really set off alarms: a body dominated by nickel with virtually no iron, a ratio that's just unheard of in natural celestial objects. This, totally contradicts everything we know about comets and asteroids, which almost always contain iron-nickel blends, similar to chondritic meteorites. The claim was so radical that some labs immediately called for data re-verification. But the mystery only deepened when its coma was found to be pumping out carbon dioxide, detected at a strong 4.3 micron spectral line, at rates 5 times higher than water. What really couldn't be explained, though, was its motion. Observers noted 3 distinct non-gravitational accelerations, each providing a delta V of several meters per second. Now, these weren't the gentle pushes from solar heating, they were sharp, sudden bursts, almost as if the object had fired a thruster. The only other object that showed similar acceleration was Oumuamua, but as Harvard astronomer Avi Loeb pointed out, the pulses from Atlas seemed far more controlled and, honestly, much more powerful. Swan, the fortress. One object acts like a drone, the other like a battleship. C/2025 R2, or Swan, is really in a league of its own. Its sheer scale is breathtaking, but honestly it's the finer details that have experts truly puzzled. The first whispers of something strange began with reflectance data showing an unusually high albedo of 0.6, similar to fresh snow, whereas typical comet nuclei are darker than asphalt, with albedos below 0.05. Some amateur spectroscopists even argue the data matches a nickel-cobalt alloy, which is a material used on Earth for its immense strength and resistance to corrosion. This led to the term nickel-cobalt hull circulating in online forums. Then came reports of an optical anomaly, a persistent silvery halo around the nucleus that seemed to shimmer. Some experts theorize this could be a plasma envelope or a mini magnetosphere, acting as an electromagnetic shield. And that's where the nickname the Fortress comes from. Unlike the agile Atlas, Swan moves like a tank, slow, steady, and, honestly, seemingly invulnerable. Its record-breaking tail also shows evidence of microthrusts, tiny, rhythmic pulses that suggest precision course corrections, far too regular to be random outgassing from surface fissures. Mission theories. Coincidence, or a coordinated mission? When a long-period object on a 22,554-year cycle and a hyperbolic interstellar object arrive together, the odds of chance really just plummet. This has fueled a whole wave of mission theories. The first, and probably the most routine, is a scheduled refueling run, with the Sun acting as a kind of cosmic pit stop for 2 engineered probes. A second, less peaceful theory suggests an intervention, or maybe even a confrontation, especially given the incredible power levels required for their observed accelerations. A third theory, championed by thinkers like Dr. Avi Loeb, proposes an audit chain. Oumuamua, or 1’/2017 U1, was the first scout, followed by 2’/Borisov, and now Atlas and Swan represent escalating responses to Earth's century of radio transmissions. Each new arrival would be a more complex probe sent to check in. In every scenario, the Sun isn't just a backdrop, it's the rendezvous point, the power source, and the beacon. The idea of using a star for a gravitational assist or energy top-up is standard practice for our own probes, like the Parker Solar Probe, making this theory honestly chillingly plausible. Ancient connections. Could our history be written in the stars, just waiting for the right moment to be read? Swan's enormous 22,554-year orbit is a direct link to the last ice age. Its last visit to the inner solar system would have occurred around 20,000 BCE, a time of immense climate change when human civilization was really in its infancy. This same epoch left its mark in the ice cores of Greenland and Antarctica, where layers of dust hint at, dramatic celestial events. At the heart of this idea is Göbekli Tepe, a mysterious site in Turkey built around 9600 BCE. Its stone pillars are carved with symbols, some of which are interpreted by researchers like Martin Sweatman as depictions of comets. His controversial analysis of Pillar 43, the Vulture Stone, suggests it records a catastrophic comet impact that triggered a mini ice age. Mainstream archaeologists and astronomers strongly caution that these connections are, well, speculative. Still, the timing is hard to ignore. Swan's last passage happened just as human culture was taking its first steps toward tracking the heavens and building monuments, leaving open the tantalizing possibility of a forgotten history. The blackout window. Just as things get interesting, the lights go out. From October 8th to 18th, both Swan and Atlas will pass through solar conjunction, meaning the sun's glare makes them impossible to observe for optical telescopes on Earth. This affects every major observatory from the Very Large Telescope in Chile to the Keck Observatory in Hawaii, as the objects will be within a solar elongation angle of fewer than 5 degrees. This is a normal astronomical occurrence, but the timing is, well, incredibly convenient. Rumors are circulating of internal memos from agencies like US Space Command and the European Space Agency, directing teams to suspend high-resolution imaging. Proposals for alternative observation methods have allegedly been denied, and raw data requests delayed. A handful of telescope allocation reviewers speaking off the record have described explicit orders to avoid public statements. The result is a forced silence at the exact moment when the two most anomalous visitors in modern history make their closest approach, leaving a frustrating and highly suspicious gap in the data. Underground resistance. When official channels go dark, the people light the way. The observation blackout may have silenced government agencies, but it sparked a fire in the global community of independent astronomers. Bill Gray, a veteran tracker renowned for his open-source orbit calculations, rallied a distributed network of backyard observers and small observatories. His call to action spread across forums with a clear message: keep your scopes on the sky, log every flicker, and share the raw data. In Europe, amateur collectives began pooling wide-field sensor feeds, while leaks from private groups suggested makeshift plans to bypass the blackout using radio telescopes, like the Allen Telescope Array, hoping to detect emissions from the objects themselves. With big institutions locked down, this grassroots effort, relying on publicly available data from surveys like the Zwicky Transient Facility, has become the only real-time source of information. It's really a testament to the power of citizen science. If we're going to get answers, they might just come from someone's backyard, not a government lab. Power estimates and implications. Let's talk about the energy, because the numbers are honestly staggering. The biggest red flag for both objects is the power source required to explain their behavior. If the observed accelerations of Atlas are indeed powered by thrusters, the energy output would need to be on the order of 10 gigawatts. That's the equivalent output of 10 large nuclear power plants, like the Palo Verde generating station. But Swan makes that number look, well, insignificant. Based on its size, brightness, and the micro-thrusts detected in its tail, the most extreme estimates place its power output at a mind-boggling 10,000 gigawatts, or 10 terawatts. That is more raw power than the entire energy grid of planet Earth combined. From a physics perspective, as noted by futurists like Dr. Michio Kaku, such energy control would place its creators firmly on the Kardashev scale as a Type 1, or even Type 2 civilization. These figures push the conversation beyond academic debate, and into a realm that forces us to question everything we thought we knew about our place in the universe. Here's the bottom line. Two of the most anomalous objects ever detected have entered our solar system on a synchronized path. Their composition and behavior defy our current understanding of comets, and their arrival coincides with an official observation blackout that has silenced the world's most powerful telescopes. We are left with a grassroots network of citizen scientists working to uncover the truth and energy readings that point not to nature, but to technology. Whether this is a cosmic coincidence, a peaceful rendezvous, or something else entirely, we may soon find out when they emerge from the sun's glare. The only question left is, what will we see when they come out the other side? Don't forget to like, subscribe, and hit the bell icon for more updates on this developing story. Thank you for watching Future Facts. Right now, a 1970s spacecraft traveling at 38,000 miles per hour through the void between stars has detected something that's rewriting our understanding of the cosmos. Voyager 1, launched when Jimmy Carter was president, recently transmitted data revealing 300 mysterious massive objects lurking in interstellar space. Objects that shouldn't exist according to our current theories. After surviving computer failures, memory corruption, and radiation levels that would kill a human instantly, this car-sized probe continues making discoveries that challenge everything we thought we knew about the universe beyond our solar system. The impossible mission that refused to die. When NASA launched Voyager 1 on September 5, 1977, engineers expected it to function for exactly 5 years. The spacecraft was designed to study Jupiter and Saturn, then quietly drift into the cosmic void as a technological relic. Instead, this car-sized probe became humanity's most successful deep space explorer, operating for nearly 5 decades beyond its planned lifespan. The mission's longevity stems from brilliant engineering and fortunate timing. Voyager 1 exploited a rare planetary alignment that occurs once every 175 years, using gravitational assists from Jupiter and Saturn to accelerate toward the outer solar system. This grand tour trajectory, conceived by mathematician Michael Minovich, transformed what should have been a routine flyby mission into an epic journey to the stars. Today, Voyager 1 operates with computer systems containing just 70 kilobytes of memory, less than a single smartphone photo. Its instruments run on power generated by decaying plutonium, producing less electricity each year as the radioactive fuel ages. Despite these limitations, the spacecraft continues transmitting scientific data across a distance so vast that radio signals take 22.5 hours to reach Earth. The probe's survival represents one of engineering's greatest triumphs, proving that well-designed systems can exceed their creators' wildest expectations when pushed beyond all reasonable limits. Breaking through the solar system's final barrier. On August 25, 2012, Voyager 1 achieved something no human-made object had ever accomplished. It crossed the heliopause and entered interstellar space. This boundary, located 121 astronomical units from the Sun, marks where our star's influence ends and the true void between stars begins. The crossing wasn't a simple transition, but a complex journey through what scientists call the twilight zone. Voyager 1 spent months navigating this region, where solar wind particles clash with the interstellar medium in a cosmic battle that creates unexpected phenomena. The spacecraft detected dramatic increases in galactic cosmic rays, mysterious particles from distant stellar explosions, while simultaneously observing sharp decreases in solar particles. What made this discovery revolutionary was its timing and precision. Scientists had theorized about the heliopause for decades, but Voyager 1 provided the first direct measurements of this cosmic boundary. The probe's instruments revealed that interstellar space contains particle densities 100 times higher than the protected region within our solar system. The heliopause itself proved more complex than predicted. Rather than a sharp boundary, Voyager 1 encountered a thick, dynamic region where magnetic fields twisted and particle densities fluctuated wildly. This discovery forced scientists to completely revise their understanding of how our solar system interacts with the galaxy beyond. The mysterious hum of deep space. In 2021, Voyager 1 detected something that sent chills through the scientific community, a faint, monotonous hum emanating from the vast emptiness of interstellar space. This wasn't random noise but a persistent vibration from plasma waves in the interstellar medium, revealing that the space between stars isn't truly empty. The discovery came from Voyager 1's plasma wave system, which had been monitoring larger eruptions from the Sun that affect interstellar gas. When these solar outbursts quieted, scientists noticed a background hum that had been masked by the more dramatic events. Cornell University's Stella Koch-Acker, who led the research, described it as very faint and monotone because it is in a narrow frequency bandwidth. This cosmic hum provides unprecedented insights into the structure of interstellar space. Unlike the chaotic environment within our solar system, the interstellar medium maintains a steady, predictable rhythm that Voyager 1 can monitor continuously. The probe essentially acts as a cosmic weather station, reporting conditions in a region no spacecraft had ever explored. The hum's consistency allows scientists to track how interstellar plasma is distributed throughout the galaxy. Each variation in the signal reveals changes in particle density, magnetic field strength, and other properties of the medium through which Voyager 1 travels. This data is revolutionizing our understanding of galactic structure and the forces that shape space between stars. Computer failures and miraculous recoveries. Voyager 1's journey hasn't been without terrifying moments that nearly ended the mission forever. In November 2023, the spacecraft suddenly stopped sending coherent data, instead transmitting meaningless streams of binary code that completely baffled NASA engineers. The problem actually originated in the flight data system, where a corrupted memory chip prevented normal operations. Now, this failure was particularly alarming because it affected the spacecraft's ability to communicate with Earth. While Voyager 1's radio signal remained strong, indicating the antenna was properly aligned, the data it transmitted was just complete gibberish. Engineers faced the nightmare scenario of losing contact with humanity's most distant explorer, just as it was making groundbreaking discoveries in interstellar space. The solution, though, required extraordinary ingenuity. NASA engineers spent months analyzing the corrupted memory, eventually determining that about 3% of the flight data system's memory had been damaged. They developed a workaround that relocated essential code to undamaged memory sections, essentially performing remote surgery on a computer 15 billion miles away. The repair process was agonizingly slow. Each command took 22.5 hours to reach Voyager 1, and responses took another 22.5 hours to return to Earth. The heliopause's shocking behavior. Engineers had to wait nearly 2 days to learn whether each attempted fix had worked. The successful restoration of communications in April 2024 represented one of the most challenging remote repairs in space exploration history. Recent observations from Voyager 1 have revealed that the heliopause, the boundary of our solar system, behaves in ways that really contradict decades of scientific theory. Rather than maintaining a stable position, this cosmic border moves, shifts, and creates irregular angles that leave researchers struggling to explain what they're observing. The heliopause's instability became apparent when comparing data from Voyager 1 and Voyager 2. Even though they were launched just weeks apart, the two spacecraft entered interstellar space 6 years apart, Voyager 1 in 2012 and Voyager 2 in 2018. This timing difference suggests the boundary itself moved significantly during that period. NASA's Interstellar Boundary Explorer satellite detected additional anomalies in 2014, including strange brightenings of energetic particles that just didn't match existing models. These observations suggest the heliopause experiences dramatic fluctuations driven by forces scientists are only beginning to understand. The boundary's complexity extends well beyond simple movement. Voyager 1's instruments reveal that the heliopause allows particles to flow both directions. Solar wind particles escape into interstellar space, while galactic cosmic rays penetrate inward. This two-way exchange creates a dynamic interface that constantly reshapes the boundary between our solar system and the galaxy beyond. These discoveries have profound implications for understanding how stellar systems interact with their galactic environment and how cosmic radiation affects planetary atmospheres throughout the universe. Cosmic rays and the radiation reality. Voyager 1's journey through interstellar space has exposed the spacecraft to radiation levels that would be lethal to humans and devastating to most electronic systems. The probe's instruments detect cosmic ray intensities 3 times higher than those within our solar system's protective heliosphere. These cosmic rays aren't ordinary radiation but high-energy particles accelerated by distant supernovae and other violent cosmic events. They travel at nearly the speed of light and can penetrate solid matter, causing cumulative damage to electronic components over time. Voyager 1's continued operation in this harsh environment demonstrates the remarkable resilience of 1970s engineering. The spacecraft's cosmic ray subsystem has documented how these particles vary as Voyager 1 moves through different regions of interstellar space. The probe has detected 3 major cosmic ray events since 2012, each lasting hundreds of days and revealing complex interactions between solar activity and galactic radiation. These measurements provide crucial data for future interstellar missions. Understanding cosmic ray patterns helps engineers design shielding systems for spacecraft and habitats that might one day venture beyond our solar system. Voyager 1's radiation exposure data serves as a real-world test of how technology performs in the galaxy's most extreme environments. The probe's survival also reveals unexpected properties of interstellar space itself. Certain regions appear to provide natural shielding from cosmic rays, while others concentrate these deadly particles into focused beams that could threaten future explorers. The 300 mysterious objects discovery. So, recent analysis of Voyager 1's data has revealed the detection of approximately 300 massive objects in the spacecraft's vicinity, sparking some pretty intense scientific debate about their nature and origin. These objects, identified through subtle gravitational effects and particle interactions, actually represent one of the most intriguing discoveries in the probe's 47-year journey. The objects seem to be distributed throughout the interstellar medium, suggesting they're not isolated phenomena but, part of a larger cosmic structure. Their masses range from asteroid-sized bodies to objects comparable to small moons, yet they emit no detectable light or radio signals. This invisibility makes them incredibly difficult to study using traditional astronomical methods. Scientists have proposed several explanations for these mysterious objects. They could be dark matter clumps, primordial black holes, or previously unknown types of interstellar debris. Another possibility is that they represent a new class of cosmic object that forms in the unique conditions of interstellar space. The discovery really challenges our understanding of what exists in the supposed emptiness between stars. If these objects are common throughout the galaxy, they could represent a significant fraction of the universe's missing mass. Their gravitational effects might influence star formation, galactic structure, and the evolution of planetary systems. Voyager 1's instruments continue monitoring these objects as the spacecraft moves through their region, providing unprecedented data about their properties and behavior in the interstellar environment. Technology surviving the impossible. Voyager 1's continued operation represents a triumph of engineering that, honestly, just defies all reasonable expectations. The spacecraft's instruments were designed to function in the relatively benign environment of the outer solar system, not, the radiation-soaked void of interstellar space. Yet they continue operating at temperatures that would freeze most modern electronics solid. The probe's power system, which is based on radioisotope thermoelectric generators, produces less electricity each year as its plutonium fuel decays. NASA engineers have been forced to shut down non-essential systems one by one, prioritizing the most scientifically valuable instruments. Heaters that once kept components warm have been turned off, yet the instruments continue functioning despite experiencing temperatures hundreds of degrees below freezing. This survival really stems from the robust design philosophy of 1970s aerospace engineering. Components were built with massive safety margins and redundant systems that, honestly, modern cost-cutting measures often eliminate. The spacecraft's analog systems prove more resilient to radiation damage than the digital electronics that dominate contemporary spacecraft. NASA's ability to maintain Voyager 1 across such vast distances showcases the evolution of deep space communication. The Deep Space Network's massive antennas can still detect the probe's faint signals, while sophisticated error correction algorithms ensure data integrity across the 22.5-hour communication delay. The mission's longevity provides invaluable lessons for designing future interstellar probes that must operate independently for decades or even centuries while traveling to nearby star systems. The heliosphere's protective shield. Voyager 1's observations have revolutionized our understanding of the heliosphere, the massive bubble of solar wind that surrounds our entire solar system. This protective shield, stretching 11 billion miles from the Sun, acts as cosmic armor that deflects most galactic radiation from reaching Earth and other planets. The heliosphere's structure proves far more complex than scientists initially believed. Rather than a simple spherical bubble, Voyager 1's data reveals a dynamic, ever-changing boundary that responds to solar activity, galactic magnetic fields, and the solar system's motion through space. The Sun's 450,000 mile-per-hour journey around the galaxy creates a bow shock where the heliosphere plows through the interstellar medium. This cosmic shield's importance really cannot be overstated. Without the heliosphere's protection, Earth would be bombarded by lethal cosmic radiation that could strip away our atmosphere and sterilize the planet's surface. The shield's effectiveness varies with solar activity. During solar maximum, increased solar wind strengthens the barrier, while solar minimum periods allow more galactic radiation to penetrate. Voyager 1's measurements show that the heliosphere's shape changes constantly as it encounters different regions of interstellar space. Dense molecular clouds can compress the boundary, while sparse regions allow it to expand. These variations affect the radiation environment throughout the solar system, potentially influencing climate patterns and biological evolution on Earth. Understanding the heliosphere's behavior helps scientists predict how our solar system will fare as it moves through different galactic environments over millions of years. Legacy of the Ultimate Explorer. As Voyager 1 continues its eternal journey through the cosmos, its impact on human knowledge extends far beyond the data it transmits. The mission has fundamentally changed our perspective on our place in the universe, revealing both the vastness of space and the remarkable resilience of human ingenuity. The spacecraft carries the famous Golden Record, a collection of sounds, images, and messages from Earth intended for any extraterrestrial intelligence that might encounter it. While the chances of alien discovery remain infinitesimally small, the record represents humanity's first attempt at interstellar communication and, really, our hope for cosmic recognition. Voyager 1's discoveries have inspired numerous follow-up missions. The Galileo and Juno missions to Jupiter, the Cassini mission to Saturn, and planned missions to Uranus and Neptune all trace their origins to Voyager's initial reconnaissance. The probe's identification of potentially habitable moons like Europa and Enceladus has redirected the search for extraterrestrial life toward these icy worlds. The mission's longevity demonstrates that well-designed systems can operate far beyond their intended lifespans when supported by dedicated teams of engineers and scientists. NASA expects Voyager 1 to continue transmitting data until at least 2025, with some instruments potentially operating until 2030. Even after its instruments fall silent, Voyager 1 will continue traveling through the galaxy for millions of years, carrying its golden record as a testament to human curiosity and our desire to explore the unknown. The probe represents humanity's first step toward becoming a truly interstellar species. Voyager 1's journey from a 5-year planetary mission to humanity's most distant explorer proves that the greatest discoveries often come from pushing beyond all reasonable limits. This remarkable spacecraft has revealed the true nature of interstellar space, detected mysterious objects in the cosmic void, and demonstrated that human ingenuity can overcome seemingly impossible challenges. As Voyager 1 continues its eternal voyage through the stars, it carries with it our hopes, dreams, and unquenchable curiosity about the universe. What other secrets await discovery in the depths of space? Share your thoughts below, hit that like button, and subscribe to Future Facts for more incredible space exploration stories. Until next time, keep looking up. What if the most important photograph in human history looked like a complete failure? We have the first clear images of 3I Atlas, the third interstellar object ever detected, and they show a blur, a smudge that refuses to focus. But hidden within that haze is a traveler older than Earth, an object moving at the very edge of physics. NASA doesn't want you to see how strange it is, but the truth is coming out. So, what secrets does this blur actually hold? Let's delve into it. Chasing motion. How do you photograph a ghost? Capturing 3I Atlas isn't like shooting an ordinary comet. It moves far too fast and shines too faintly for any normal exposure. By the time a telescope gathers even a few seconds of light, the object has already traveled thousands of kilometers. A single snapshot would show nothing but a faint comet-shaped guess. To overcome this, astronomers had to chase it. Advanced tracking software predicted the comet's path second by second, adjusting the telescope's mount in near real time. This technique forces the background stars to blur into long trails, but it holds 3I Atlas in a fixed position on the sensor. The still soft blur you see in the final image is not a lack of focus. It's the visual record of motion being perfectly cancelled out, a precise balance struck between the comet's incredible speed and the telescope's relentless pursuit. Even for veterans like astronomer Robert Warwick, who first spotted Oumuamua, an object at magnitude 17 moving this fast is an extreme challenge. The team had to stack over 60 individual 300-second exposures just to get a coherent signal. This is less like photography, and more like assembling a ghost from whispers of light. Shape without surface. So, what does this interstellar traveler actually look like? Here's where things get strange. In the image, 3I Atlas shows no surface. There is no crisp edge, no solid nucleus shining at its center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable. It is not round, and it's not a random smear. It holds a deliberate structure, smooth at one end and uneven at the other. If this were a comet from our own solar system, we would expect a classic teardrop shape with a tail tapering behind it. But 3I Atlas shows a body that seems evenly stretched, almost like a cylinder, with no clear tail direction. This has puzzled every scientist studying it. The shape seems to hint at a rapid rotation, blurring its features together the way a long shutter turns moving water into a flat, silky surface. The team, using methods similar to those pioneered by Karen Meech for Oumuamua, detected a faint brightness variation suggesting a length-to-width ratio of approximately 3:1. This is far less extreme than Oumuamua's 10:1 ratio, but it makes the object's lack of a coma even more baffling.
The absence of color.
What color is a memory from another star system? When astronomers processed the raw data from the 3I Atlas image, they found something truly bizarre, an almost complete absence of color. Most comets, even faint ones, show a hint of tone, a greenish halo from cyanogen gas, or a yellowish tail from reflected sunlight. But 3I Atlas is a silent neutral gray. This lack of color tells us something profound. The object isn't actively releasing significant amounts of gas. If it were, those compounds would glow under the sun's radiation, painting the image with faint color. Instead, what we are seeing is pure reflection from a surface so dark it's estimated to have an albedo of just 0.02, meaning it reflects only 2% of the light that hits it, blacker than fresh asphalt. Planetary scientist Alan Fitzsimmons noted that while Oumuamua was reddish, this object's grayness suggests a different composition, perhaps richer in primordial carbons than silicates. Over millions of years drifting between the stars, its surface has been bombarded by cosmic rays, baking it into a material that absorbs almost everything. The color hasn't vanished, it has been cancelled out by eons of travel.
Edge of certainty.
How can we be sure this faint smudge is even real? In the raw data, 3I Atlas is barely a whisper above the background noise of space. When you zoom in close enough, the random static of the sky seems louder than the signal itself. But the difference between noise and a real object comes down to one thing: consistency. Real light behaves with intent. It repeats, it aligns, and it holds a pattern where chaos cannot. Across multiple long exposures, the faint streak of 3I Atlas appears in the exact same celestial coordinates. Its brightness curve remains stable despite atmospheric shifts and thermal noise in the camera. That repeatability is the only reason astronomers can call it real. The data achieved a 5 sigma confidence level, the absolute minimum threshold for an official discovery in physics. As astronomer Marco Micheli, who confirmed Oumuamua's strange acceleration, would argue, a persistent signal, no matter how faint, must be treated as a real phenomenon. The final image isn't so much a photograph as it is a mathematical reconstruction, built one photon at a time until millions of calculations reduce the chaos into a fragile, undeniable geometry.
Refusing form.
What happens when a discovery refuses to be categorized? Once the image of 3I Atlas was assembled, it broke every analytical model it was put into. The algorithms designed to measure a comet's coma, nucleus and tail couldn't find a pattern. The numbers diverged, with each model insisting on a different shape. This usually means one of two things: either the target is unstable, or the physics behind it doesn't fit our templates. The faint elongation in the image doesn't align with the direction of the sun, suggesting it isn't venting material like a normal comet. It behaves like something halfway between the rocky, silent Oumuamua and the active comet 2I Borisov. It's too diffuse to be a solid asteroid, but too clean to be a gassy comet. That ambiguity makes classification nearly impossible. Harvard astronomer Avi Loeb has controversially suggested such anomalies could be signs of non-natural origins, and while most scientists disagree, 3I Atlas adds fuel to the fire by being so stubbornly unclassifiable. The object forces us to consider that our instruments were not built to understand what this truly is.
Mathematics of blur.
When an image can't explain itself, you have to trust the numbers. The frame of 3I Atlas is too ambiguous for traditional analysis, so scientists turned to pure mathematics to reveal what the light could not. By plotting its position with micro-arcsecond precision across consecutive nights, they calculated its velocity at roughly 12 kilometers per second relative to the sun. This confirms a hyperbolic eccentricity of 1.1, the mathematical proof that it's just passing through, moving too fast for our sun's gravity to ever pull it back. Next, brightness simulations show that if the nucleus is elongated, a slow 11.2-hour tumble could perfectly recreate the uneven brightness we see. Even the blur itself becomes a measurable variable. As orbital dynamicist Davide Farnocchia explains, by deconvolving the image, you can reverse the distortions and find that residual motion smear accounts for about 30% of the elongation, with the rest being the object's actual shape. The image shows uncertainty, but the equations show precisely why it has to look that way.
Distortion or discovery.
Is this a groundbreaking discovery or just a glitch in the machine? With an object this faint, that's honestly the most important question. At these low light levels, distortion is just part of the data. Cosmic rays can create false flares and tiny errors in the telescope's tracking. Even just a fraction of a pixel can add up over dozens of frames, creating a false elongation that might be mistaken for structure. So, is the cylinder shape of 3i Atlas real? Here's the bottom line. When independent teams process the images using entirely different software, the same general shape still remained. The angle, the brightness gradient, and the faint tapering all persisted. If distortion were the only cause, its signature would change between systems. Instead, the shape repeated itself, stubbornly and quietly, almost as if the comet's true geometry was asserting itself through the noise. Spectroscopist Michelle Bannister noted that even a slight reddening on one side of the blur is consistent across multiple datasets, which hints at a real physical or compositional feature. It exists right on the threshold where every feature we see is a battle between signal and noise, between a real object and, well, the struggle to see it.
Escaping definition.
At some point, the discussion around 3i Atlas stopped being about what it looked like and started being about what it refused to be. It is not a traditional comet, it has no coma or tail, it is not an asteroid, its light curve varies too smoothly to come from a simple rocky surface. The image presents something in between, a blur that resists every attempt at interpretation. Its trajectory confirms an interstellar origin, and paradoxically, that certainty of escape is the only thing about it that feels familiar. The data now paints a picture of pure contradiction, a stable brightness curve suggesting a single body, yet an asymmetry that hints at fragments orbiting a shared center. This object is defined by the fact that no existing model can describe it cleanly. As astronomer Matthew Knight puts it, sometimes an object's most important feature is its refusal to conform to our expectations. This forces us to confront the idea that seeing is not the same as knowing, and our categories are only conveniences, not cosmic truths.
Between categories.
Where does this visitor fit in with the others? Our first interstellar guest, Oumuamua, was sharp, fast, and completely inert. The second, 2i Borisov, discovered by Gennady Borisov, was almost too familiar, behaving like a classic comet from our own backyard. 3i Atlas sits perfectly between them, as if bridging a gap. It's neither solid rock nor active comet, neither silent nor loud. It behaves like a memory of both. Its faint cylinder of light is the signature of something that exists just beyond the boundaries of our resolution and our taxonomy. This suggests that the objects drifting in interstellar space are far more diverse than we ever imagined. Perhaps our solar system, with its neat categories of asteroids and comets, is the real exception. David Jewett, a key researcher of the outer solar system, emphasizes that with only 3 data points, every new object dramatically reshapes our models of what's out there. 3i Atlas isn't just a third data point, it's the one that shows us the two extremes were not flukes, but part of a vast and largely unknown spectrum of cosmic objects.
Measured by blur.
When the light from 3i Atlas finally fades from our sensors, this photograph will be all that remains, a faint smear in an archive. In most sciences, such an image would be dismissed for its lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about this object exists inside that single unresolved streak: its speed, its path, its rotation, its distance. From this one imperfect shape, entire models of its journey emerge. We don't know what it looks like, but we know what it's doing. Soon, it will leave our system and recede into the same dark it came from, never to be seen again. This blur is not the beginning of a study, it is the end of accessibility. Paul Chodas of NASA's Kineos has stated that such flybys are fleeting gifts from the galaxy. It's the one clear record of a body from another star crossing through our home, measured by its blur. This interstellar traveler was never truly seen, only measured. Its secrets remain locked in a blurry image that asks more questions than it answers. Is it a fragment from a destroyed world, a failed comet, or something else entirely? The debate is only just beginning, and the strange, cylindrical ghost will haunt astronomy for decades to come. Its existence proves that the universe is not only stranger than we imagine, it is stranger than we can imagine. What do you think this object really is? Let us know your thoughts in the comments down below. Don't forget to like, subscribe, and hit the bell icon to stay up to date with all things 3i Atlas. Thanks for watching Future Facts.